Hello again, Physics 30s. In today's lesson, we're going to continue discussing what happens when you put a current carrying wire through a magnetic field. And we'll do that by looking at a second application, that being how an electric motor works, specifically a really simple direct current electric motor. No need to restate the learning outcomes from the program of studies because they are just identical to the ones from last time. What I'm going to do is I will first of all talk about the different parts or components of an electric motor, and then discuss how the electric motor operates, like how it actually rotates. And then finally, we'll just quickly look at what can be done to make the motor operate as efficiently as possible. On the screen, you can see the different parts of a simple direct current electric motor, and we'll focus on three segments before we start to talk about how the motor actually works. So we have one, the stator. We have two, a part called the armature. And then three, we have a section that's called the commutator. Stator is pretty simple. In the diagram that you can see on the screen, the stator is just a couple of large bar magnets, and the point of the stator is just to provide an external magnetic field. In this case, it's a couple of large permanent magnets. I suppose an electromagnet like a solenoid could generate it as well, but we'll just focus on this simple illustration where we have a north pole and a south pole, and those two bar magnets producing a magnetic field. And like I said, that's the point of the stator, is simply to generate an external magnetic field. Component two, which is called the armature or the rotor. And I can just highlight what this segment looks like. So it starts here. Trace it all along. Okay, so that segment in red is what I would refer to as the armature or rotor. And all the armature or rotor is it's a loop that is going to rotate. And it's a loop that's made up of a bunch of conducting wires. The way I showed it in the illustration, it looks like there is just one wire that goes through the actual armature. In reality, I think it can be like a bunch of loops of wire. It's not restricted to just being a single loop. So for example, I could have another loop that's just in parallel to this red wire, where I could have like a purple wire that runs just right beside it. I suppose the wires probably shouldn't cross, but it's okay. Just trying to point out that inside the armature, you can have a bunch of wires that are side by side. And we'll talk about why it's important to have more than just a single loop of wire once we get towards the end of the lesson. All right, so that's the armature. The final part is the commutator. What the commutator is it's a metallic ring, and in the middle of the ring, it's split. So if I look at the illustration, let's pick a different color so it stands out a bit more. Vertically, I can see that the ring is split. The reason for this split is, let's look at the direction of electron flow. So this commutator is connected to a wire that's connected to a battery. The short end means the negative terminal of the battery. The long end means the positive terminal. So let's look at the direction of electron flow. So electrons would flow away from the negative terminal and towards the positive terminal. So my electrons would flow outward along this wire, and then they're going to enter the commutator. What this split ring does is the electrons cannot jump across the split ring. If they could just jump across the split rings, they could perhaps just simply go right across and then go back into the positive terminal. But since that ring is split, they have to take a different path to get there. So the different path they're going to have to take is to pass through the armature, go all the way through the armature, and then we'd come back into the right side of the commutator, and then finally we would get over to the positive terminal of the battery. So essentially what the commutator is doing is it's forcing the electrons to go through the armature. In terms of how this works, well, we can actually apply the third-hand rule to figure out the operation of this. So I'm going to start off by drawing a three-dimensional Cartesian grid. So let's say that vertically up is going to be the y-axis. We'll say at an angle that's down and towards the right. This would match up with this segment of the armature that's up at the top here. That's in the x direction. And then we have my other part of the grid, which would point in the z direction. That would be matching the direction of these green arrows attached to the electron flow. Okay, so let's look at the left-hand side of the armature. And what I want to do is I want to use my third-hand rule to predict what direction is the magnetic deflecting force going to be on that section of the armature. So, electron flow means use your left hand. The magnetic field, external magnetic field, is represented by the direction your fingers are going to point. If you look at the illustration, I'll draw the magnetic field lines in red. The magnetic field lines would go out of the north into the south. I'm just going to draw one field line through. So we go out of the north into the south. That's one of my magnetic field lines. If I follow that up with my Cartesian grid, that would mean that the magnetic field points in the positive x direction. Your direction of current or electron flow, so we'll do, that's supposed to be an E negative. The direction of electron flow is represented by your thumb. If I looked at this side of the armature, where I have this little black dot, the direction of electron flow through that part of the armature would be along the z-axis, specifically be in the negative z direction. And what I want is I want the direction of the magnetic deflecting force, which is Fm. The direction of the deflecting force is going to be the direction that your open palm is going to face. And all these characteristics together make up my third-hand rule for current. Okay, let's see if we can do this. So start off with your left hand. Make sure your thumb and your fingers are perpendicular to each other. I'd start off by taking my fingers and pointing them in the direction of the x-axis, the positive x-axis. Then you have to rotate your wrist, so you'd have your thumb pointing in the direction of the negative z-axis. And if you do this correctly, I believe your palm should be facing towards you. Your open palm should be facing towards you. And your open palm towards you should be the positive y direction. So positive y direction. And if we drew the magnetic deflecting force vector on this side, I'd have Fm that's pointing in the positive y direction. If I go to the opposite side, I'm not going to rewrite all the different steps again, but I also want to predict what direction the magnetic deflecting force is on this side. Your magnetic field still points in the same direction. The magnetic field is pointing in the positive x direction. The difference here is now the direction of electron flow has been reversed, so now it's going to point in the positive z direction. So to predict the direction of the magnetic deflecting force, again, take your left hand, because it's electron flow. I point my fingers along the positive x direction. This time your thumb has to point in the positive z direction. And if you do this, your open palm should be facing downward away from you, which means it would be in the negative y direction. And if we draw that magnetic deflecting force vector, Fm, that would point down. Now, in terms of how the actual armature rotates, initially you might look at this and think, okay, so there's two forces acting on the armature. One is in the positive y direction, one is in the negative y direction. If I find the sum of those two forces, that would just be equal to 0. Wouldn't that mean that the armature does not rotate? Not quite. So what I'm going to do is I'm going to draw a side view perspective of the armature and the commutator. So let's do side view. So let's say here's my split ring. And from a side view perspective, I would just see this portion of the armature. And I would see this right portion of the armature. If I draw my forces on here, on the left-hand side, I'd have my deflecting force that points up. On the right-hand side, I'd have my deflecting force that's pointing straight down. I'm going to relate this back to how we were talking about the operation of a current balance, specifically dealing with torque. And torque is a force that causes twisting. So let's think about this as like this armature is being like rested on a fulcrum point, kind of like a teeter-totter. So here's the fulcrum of my teeter-totter. If I said to you, the only force acting on the teeter-totter is at the left end, and that force points straight up, what rotational direction would that force cause the armature or the teeter-totter to rotate? Well, if you grab this end and you pulled straight up, it should cause the armature to rotate in a direction that would be clockwise, CW. If you look at the right-hand side, and I said if Fm is the only force acting on the armature, what direction would this force cause the armature to rotate? If I pulled straight down the armature, it would also cause the armature to rotate in a direction that is clockwise. What these two forces do is they generate torque. Torque is a force that causes twisting in a specific rotational direction. Both of these forces generate clockwise torque. So what would happen is this would cause the commutator to rotate in a direction that is clockwise. So they both work together to give you this clockwise rotation. So as a result of the armature through the magnetic field, the deflecting forces generate torque. This torque generates this twisting force, which causes the armature to rotate. And in a nutshell, that's how an electric motor works. Now, what this explanation does not do is it does not explain the purpose of the split ring commutator. So we're going to address that now after we quickly just summarize the points of how the motor works. So how does it work? There are magnetic forces on opposite sides of the armature. They're equal in magnitude, they're opposite in direction. Well, we showed that in the previous slide. On the left-hand side, the magnetic force was up. On the right-hand side, it's down. They're both equal in magnitude, opposite in direction, and they generate clockwise torque, causing the armature to rotate. To explain the function of the split ring commutator, let's just consider what would happen if you did not have the split ring commutator. In this illustration, it does not show a split ring commutator. What the illustration shows is that you have one end of the armature connected to a negative terminal, and you have the other end, I'll pick a different color, is connected to a positive terminal. Now, this is going to cause the armature to rotate in a direction that is going to be clockwise. Let's say we don't have the commutator and we're just going to have the armature rotate in this clockwise direction. And let's rotate through half a revolution. So let's go through 180 degrees and see what this looks like then. 180 degrees later, you would then have the part of the wire connected to the negative terminal on the right-hand side, and you would have the part of the battery terminal connected to the armature now on the left-hand side. If we follow the direction of electron flow through the armature, you're going to see that it's now reversed. So in case one, this is the one we dealt with initially, the direction of electron flow went first of all kind of like an upward direction, right, and then downward, depending on our perspective. And in this other situation, if the battery rotates along with the armature, then the direction is going to reverse. Now, this creates a problem, because if we go back to a little diagram of the armature, just doing like a side view. So let's say we have the commutator. We've gone through 180 degrees rotation. And now, because the direction of current is reversed, and if you use the third-hand rule, that's going to cause the direction of the deflecting forces to reverse. So on the left-hand side, you'd then have your magnetic deflecting force down. On the right-hand side, you'd have the magnetic deflecting force up. Actually, we shouldn't draw the commutator here because I identified this is what's going to happen without the commutator. Okay, so let's pretend like the commutator is not there. Let's pretend we have this little fulcrum here, just like a teeter-totter. And if I said to you now, what rotational direction are these forces going to cause the armature to rotate? You have the pivot point here, and you pull down on the left-hand side, that's going to cause the armature to rotate in a direction that is now counterclockwise. And if you pull on the right end of the armature straight up, that would also result in counterclockwise torque. This is a problem. If you had the armature flopping back and forth every half rotation, you would never have continuous rotation of the armature in a specific direction. Your motor would be so brutally inefficient that it would not work. You need it to be in a continuous rotational direction. So this is a problem. We cannot have the battery rotate along with the armature, because if it does, that's going to cause the direction of torque to change every half a rotation. So this is a big problem. Every half rotation, your armature would then flop back and forth, which is not what we want. Now, in terms of how the commutator works, I'll read these bullet points out. Then what I'm going to do is I'm going to show you an animation that will make the bullet points hopefully a bit clear. So what I've said is, for continuous rotation to occur, the direction of electron flow in the loop must change every half rotation. This can be accomplished if the leads of the armature contact a different terminal every half rotation, changing the direction of electron flow. If you just read these two statements out one after another, they don't make a whole lot of sense. So I'm just going to exit the PowerPoint slide here for a moment. And I'm going to pull up an animation of an electric motor. And I'm also going to pull up a whiteboard just so I can clarify direction of, to show you like what a three-dimensional grid will look like in a moment. All right, so I can see an animation of an electric motor. And I'm just going to, these blue vertical lines, I'm assuming you can see the actual mouse cursor. These blue vertical lines represent the direction of the magnetic field. I'm just going to remove them for a moment. And then I'm just going to remove this, which just removes the direction of the magnetic force. And I'm going to pause. Let's make this thing rotate slower. I'm going to pause the armature. At this spot. Yeah, that's roughly good. Okay. So let's set up a three-dimensional grid. So in this case, we'll say that straight vertically upwards is going to represent the y-axis. And then we'll have our z-axis. That points in this direction. And then we'll do the x-axis in this direction. Now, what I want you to do is, again, I'm assuming you can actually see the mouse cursor. So this animation is showing conventional current, first things first. A conventional current would be like the hypothetical direction a proton would go, although electrical current is not the movement of protons. If you put a proton close to the positive terminal, it would repel from the positive side, go through the armature, the commutator, then through the armature, and then it would go all the way back into the negative terminal. So these red arrows here are just showing the direction of conventional current. If I click the magnetic field, that just shows what the direction of the magnetic field is. We can quickly use a third-hand rule to predict what direction the magnetic deflecting force is. I don't think I'm going to write it all out, though. So your fingers, actually, maybe I should do it. Okay, so we'll say B, which is your fingers. They would point in the direction of the magnetic field. That magnetic field direction is in the negative y direction. Let's focus on this top part of the armature. So on the very top part of the armature, the direction of conventional current flow, which is I, being represented by your thumb, would point in the negative z direction. And I want to know the direction of the deflecting magnetic force, which my palm is going to represent. Now you want to use your right hand because we're dealing with current. So right hand, if you take your right hand, make sure your fingers and thumb are perpendicular to each other. If your fingers point in the negative y direction, and your thumb points in the negative z direction, I believe your palm should be facing away from you, which would mean that the magnetic deflecting force would be in the positive x direction. And let's check to see what direction it shows. And it does. At the very top of the armature, it does show the magnetic deflecting force pointing towards the negative x direction. Okay, I'm going to remove the magnetic field, and I'm going to remove the direction of the magnetic deflecting force. Now, what I want you to do is I want you right now to pay attention to what direction the current is going through this top part of the armature. We're actually going to follow this top part of the armature through one complete revolution. So let's focus on this top part. So I'm going to write down top part of armature. Top part of the armature. Now at the start, which is right here, the direction of current is in the negative Z direction. So I'll say negative Z direction. What I want to do is I'm going to make this thing rotate, and I want to look at what is happening to the direction of current on this top arm right here. Okay, we're going to follow this top arm, so through like half a rotation. And I want to see what happens to the direction of current. So let's follow this top part of the armature. Okay, so it starts rotating. I want to go through half a revolution. Half a revolution is then going to be about right here. Okay, so half a revolution would be 180 degrees later. Look what's happened to the direction of current. The direction of current is now pointing in an opposite direction. So I is now in the positive Z direction. So what's happened is, what this commutator does is, if you take a specific branch of the armature, every half of rotation, 180 degrees later, it's going to change the direction of the current through that portion of the armature. I'm going to go through this one more time, and this time I want to focus on what is the closest terminal of the battery that the armature is connected to. Okay, so let's go back to focusing on this top part of the armature. This top part of the armature at the start here is closest to the positive terminal of the battery. Okay, so at the very start, connected to the positive terminal. We're going to follow this little loop through half a rotation, and I want to see what terminal it's then closest to. Okay, following it, that top part of the armature is now at the bottom, and then we pause it, and now that part, because of the split ring commutator, is now close to the negative terminal. Let's go back to the PowerPoint slide for a second. So what I've observed here is every half a rotation, so every 180 degrees later, the direction of current in a segment of the armature is going to reverse. And this is due to that part of the armature being closer to a different terminal of the battery. So in the notes on this slide, whoops, wrong slide. Let's try that third time. For continuous rotation to occur, the direction of electron flow in the loop must change every half rotation. Well, direction of electron flow, direction of current, it did change every half rotation. And it changed because every half rotation, the leads of the armature, which means the part of the armature we are worrying about, is then connected to a different terminal of the battery. So essentially what this is doing is the split ring commutator is just a clever way of not having the battery rotate along with the armature. And what it's doing is it's always making sure, let's remove this magnetic field, it's always making sure that whenever you have a part of the armature connected to the positive terminal at the top, the deflecting force is going to point, let's bring up the whiteboard again, is going to point in the negative x direction. And again, if I go through half a rotation, no matter what, that top part of the armature has a magnetic force in the same direction. So as a result of using the commutator, what I'm not having occur is I'm not having the direction of the magnetic force flip back and forth every half a rotation. So right now it's pointing towards the left at the top. Half a rotation later, it's still pointing towards the left. At the bottom, the direction of the magnetic deflecting force is towards the right. Half a rotation later, because of the way the commutator is set up, it's still towards the right. Because of this, this would always generate torque that I believe would be in a direction that's counterclockwise about the split ring. And I believe we can see that from our perspective. We can see the armature rotating in a direction that is counterclockwise. So a little bit difficult to see. I mean, it's probably most easily understood if you just kind of just watch the animation and play around with it a little bit. I'm not sure if you can see the name of the website at the very top right here. I tried to highlight it if you did want to. If you can't see it, like I would just go to the website that's called, I'd type in like Walter Fent applets. And then I would look for direct current. Electric motor. And then you can see, you can play around with the animation, then you can hopefully get a better sense of how that split ring commutator is working. And again, just long story short, it's just a clever way of preventing the battery from not rotating along with the armature. The battery is stationary. It's a commutator that's rotating, and it's rotating in a way that's always making sure that you're getting torque generated in the exact same direction. So we get the nice continuous rotation that we want. A few more notes. 1, not every part of the armature is going to experience a deflecting force. I'm just going to modify this picture here. So let's change the let's go make these bar magnets larger. So we'll make this guy this big, so that's my big south pole. Make this one larger. North pole. If I drew the magnetic field lines here, the magnetic field lines go from north to south. So I can draw a few of them. Roughly uniform, closer to the center. North to south, north to south, north to south, north to south. That's a magnetic field. Now, of these 3 wire segments, only a few of them are going to actually experience a deflecting magnetic force. If we go back to our equation for calculating the magnetic deflecting force acting on a current carrying wire, that equation was Fm. The magnitude of the deflecting force is equal to I L B times sine theta. Theta is the angle between the length of the wire and the magnetic field. If I look at the picture, segment 1 Well, that part of the wire intersects those magnetic field lines at a 90-degree angle. So there's definitely a magnetic deflecting force generated there. Same as segment 3. It's perpendicular to those magnetic field lines. Segment 2 is not. Segment 2 is parallel to the magnetic field lines. If that segment of wire is parallel to the field lines, theta would be 0, and that part would not generate a magnetic deflecting force. The total amount of wire that's actually being affected by the magnetic field is what we refer to as the active length. In this scenario, based on how I've numbered the different parts of the wire, the active length would be L1 plus L3. So if we're going to perform some calculations dealing with an electric motor, the L in this equation would just be the active length. And what that would tell you is it would tell you the total magnetic deflecting force acting on the armature. It's just magnitude. So it gives you the magnitude of the force acting on side 1 plus the magnitude of the force acting on side 2. So we can still use the equation that was derived in the previous lesson to deal with calculations related to electric motors. Let's say that you wanted to increase the magnitude of the magnetic deflecting force acting on the armature. One way you could do it, I'm just going to erase this. One way you could do it is what I illustrated initially when I was talking about like what's inside of the actual armature. So inside of the armature, you have a bunch of lengths of wire. So I'll draw one length of wire here. If you have electrical current moving through here, you'd have like a bunch of electrons that are moving through the wire. I'll draw them on one side. If I added more loops, so let's do this in a different color. Let's say we added another loop. It's inside of the armature. More loops means you'd have more electrons moving through the armature. The more electrons you have moving through a magnetic field, well, each of those individual electrons is going to experience a deflecting magnetic force. So the more electrons that pass through there, the larger the overall magnetic deflecting force would be. So rather than just having like one loop of wire going through the armature, we can have multiple loops going through the armature. That would result in a bigger deflecting magnetic force. The bigger the force, the greater the torque is that you can generate. We call that the effective length. So the active length would just account for all parts that are perpendicular to the field. If we take the active length and multiply by the number of loops, usually the variable we use to represent the number of loops is just a capital N. Then that would tell us what we have as the effective length. So the effective length would account for the active length and how many times you actually loop the wire around. And the more loops you have, the larger the deflecting force would be, the larger the torque would be. I suppose like the faster the motor would actually operate. That's the conclusion of this lesson. Complete the assignment called Electric Motors. I believe there is a challenge question attached to the assignment on this, although the challenge question itself has absolutely nothing to do with an electric motor. It has everything to do with that spiraling effect I was talking about in the lesson on the mass spectrometer. It's a tough problem. But again, if you want a bit of a hint as to how to do that, I would go back to the part of the lesson on the mass spectrometer where I was talking about the Van Allen radiation belts.